Right, so I just like to make a correction on what I said just before. I said that, okay, the scale here is 1 inch to 100 feet, so we wouldn't have hundreds of meters of Triassic. Well, they seem to think differently, because if we look here, they seem to say, okay, the Mars, for example, can be 0 to 1500 feet. So, okay, so they could be hundreds of meters. But still think it's not going to be, your cross-section is at 163,000 scale. So 1 centimeter on your cross-section is going to be 630 meters. Here we have maximum seems to be 1500 feet, which is going to be 450 meters. So, and that's really the maximum you will get over the whole map. So that means that you won't have more than 6 millimeters on your cross-section that will be made of the Triassic. So keep that in mind. It's just a shrouding of Triassic over the older units. So when we do a cross-section, we tend to fill from the youngest to the oldest. And sometimes, most of the time, we put the faults first because they tend to cut everything. They don't here, because if you look at most of the faults, they terminate in the Triassic. So most of the faults here seems to have been active before the deposition of the Triassic. So the Triassic, we're not going to represent the Quaternary here because it's complicated enough, and the Quaternary is not going to represent at that scale huge volumes. So we've got some head here, which is Quaternary deposit here. We've got this alluvium. We're going to ignore that, and we're going to just fill that valley with Triassic here. We have some volcanics in the middle of that hill here that we're going to ignore as well, just for simplicity. So this little red thing in the middle, we're going to ignore it. Just be aware it's there. And what we're going to trace first is the Triassic. So if we think about the middle of the section here, again, we've got the topography is relatively flat, as you would expect. And here we've got, just for illustration purpose, I'm representing here, so we're going to say this is north, this is south. We have rock units here which are dipping. The Carboniferous here is dipping at an angle of 20 degrees. So under that Triassic, we've got the Carboniferous that is dipping at 20 degrees. I'm exaggerating here because it's not easy to draw, but here, you know, when you look at the shape of the contours, that seems to suggest the Triassic is dipping at a lower angle than the Quaternary. So what you will have is a low angle contact like that. And it's the same on the other side. So we're going to have something like that. If you think about what's happening on the other side, the dip here is more like 65 degrees. So the units underneath seems to be dipping at a greater angle. So your Triassic is going to appear like that, and the rock units underneath will probably come, like that, just as an example, will probably come and intersect the contact this way. So here is the base of our unconformity, and if you want, you can represent the transition from the conglomerates here on the edges to the Mars in the middle. So that's for our Triassic in the middle. The Triassic appears in a couple of other places at the tips of the section. And again, it's to keep in mind that this is just a shrouding. So we have here a fault that we will think about later. I'm going to put it vertical just for now. But if you think about that transition here at the line of section, we've got the fault, and then we get into that Triassic conglomerate, and then we've got a bit of D2 here that appears just in the middle. So if we think about our line of section, the line of section is like that. We've got a fault here that I will draw vertical. Then we've got that Triassic that does something like that and like that. So that's the Triassic here, and we've got the Carboniferous that is here on the cross section. So that means this is just the Carboniferous poking through, so if you think about what that will look like on the cross section, I'm going to go like that. That's north, that's south. You've got your cross section. So this is your fault. I'm going to draw that vertical. And what we have here, so this is the map view, this is the cross section. What we have here is along that line of section, so all that is Triassic, so we've got Triassic, then we get into the Carboniferous and Triassic again. So it's as if, you know, the Triassic here is on top of the Carboniferous. Of course, it's more recent, so it's going to look like that. So this is our Triassic here. And here it's been eroded away, allowing us to see the rocks that are underneath. So again, just a little shrouding of Triassic, and here erosion allows us to see the Carboniferous, which is underneath. So if you've got some understanding of what the rocks are doing underneath, you can represent whether they're dipping, for example. But again, this is this low angle unconformity, which here appears and comes over the surface. The last point where we have the Triassic is on the other end of the section. And again, here it's another place where we have just a little amount of Triassic on top of the underlying succession. So here we're getting into, where's the line of section? It's here. So we've got a D1B, we're getting into the BO, which is it's the Brington Oolite. And then you can see that here it's a sort of little syncline, like the beds are dipping towards the south here, and then towards the north here. So we can see this is representing a syncline, and here the Triassic comes and covers part of it. So again, on your line of section, you will have your units. So this will be your Triassic, this will be your D1B, this is the Brington Oolite. So here we've got the beds are dipping at an angle, at a very low angle here. So it's like 2 degrees. So yeah, it's almost horizontal. And then you can see that we are dipping 20 degrees in the other direction. So the Triassic, again, is just that very thin layer of Triassic. And here that bed is going to come underneath and intersect the contact, the base of the Triassic here. If you didn't have the Triassic, you can see that if you didn't have the Triassic, you will find the contact between the Brington Oolite and D1B just here, just at the contact. So this is how we're going to represent this. Okay. Now let's talk about the faults. So the faults, we've got like the ones on your line of section, we've got a couple of major ones here. And then we're cutting 1, 2, 3, 4 here in that anticline. Okay, so again, as I said earlier, it's very difficult to come up with the deep angle and the deep direction when you can't really see the topography. One of the things that helps is that they've put tick marks here that represent the down-thrown side. So this here, for example, you can see that tick mark here is a tick mark here on the Brockley fault, which shows that this part of the fault has gone down with respect to this part. Similarly, we have, which one is it? There was another place. So again, that fault here, the Rington Hill fault, here we've got a tick mark here that seems to indicate that that part has gone down, though the tick mark here is the other way around. So that seems to have gone down with respect to that block and that block. And in that side, we don't really know, but you can probably tell from the relative age of the rocks. Okay, so what do we do with that? We're going to start with the southern ones because they're the easiest. Because it's written over thrust, and you can see that their shape, like they seem to be associated with, they seem to come, and this one merges with the axis of an anticline here, and this one is the same orientation. And the fact that they say over thrust seems to suggest, well, they are likely to be thrust fault that have been associated with the compression. So these ones, we're going to represent them as thrust. And if they give us an indication on the down-thrown side here, with the tick, for example, we know that these thrusts are bringing rocks from the south towards the north. So these two thrusts, we're going to make them, because they sort of follow each other, we're going to make them dip towards the south. Now, what is the angle we're going to choose for this thrust? Again, nearly impossible without more information to come up with an angle for that. But what we know is that we've got the dip of the rock units there. And we know, for example, that for a thrust fault, imagine this is flat. If we have a thrust fault, the thrust cannot be less steep than the units on both sides. So let's say that here, for example, we've got a thrust fault here. And if this is the dip of the units here, we've got a good relationship. We can see that as we move up, the rocks are getting younger and younger as we move along the thrust fault. Similarly here, as we move along the thrust fault, we're getting into younger and younger rocks. So that's because I've drawn the thrust at a greater dip angle than the beds themselves. What will happen if I did the opposite? Well, imagine we have a situation like that. I'm going to change color. Imagine I make a thrust like that, low angle, and the beds are dipping more steeply. Well, so if nothing has been inverted, if we are getting into younger rocks this way, okay, you can see that you're just now, okay, so we're bringing here